Question 22. A boy of mass 70 kg stands on the end of a diving board at a distance of 1.8 metre from the wall. Part A. Calculate the moment of the boy standing on the diving board. Gravitational field strength on Earth is 10 newtons per kilogram, or at least it is in this question. Moment equals force times perpendicular distance to pivot. So force times distance essentially, but it's a perpendicular distance. That's what makes it different to work done. Our boy has a mass, which therefore means he has a weight, and this weight is acting downwards. Thankfully, this weight is perpendicular to our distance from our pivot, which presumably is here, where our diving board is attached to the wall. So force equals the weight of the boy, which is equal to the mass times gravitational field strength. We can do that there. 70 times 10 equals 700 newtons. Perpendicular distance to the pivot, so perp distance equals 1.8 meters. That's in our standard unit of measurement too. So now we can use our equation for moment. So moment equals 700 newton times 1.8 meters, 1260 newton meter. Question 22b. The boy dives vertically into the swimming pool. The water in the pool is 3.2 metre below the diving board. Calculate the velocity of the boy when he enters the water. Use an equation from the datasheet to help you. Gravitational field strength on Earth is 10 newtons a kilogram again. Before we have a look at our datasheets, let's see what we've got to work with already. We've got a height, so 3.2 metre. We want a velocity, that's one of our unknowns. We've got gravitational field strength, that's handy, 10 newtons a kilogram. Earlier on in the question we were told the boy's mass, so we might as well note that down too. And whilst the distance from the boy to the wall is 1.8 metres, if he's dropping from there to the water, that 1.8 metres doesn't really give us anything extra. He could be standing anywhere along this board but dropping down. As we look at the datasheet, there aren't any equations that immediately jump out, apart from maybe this one which talks about final velocity and initial velocity. But it does have an acceleration which we don't immediately have, except that we do here. Now, this shows us this question can be answered in two different ways. If you successfully remember that g, the gravitational field strength on Earth, is also equal to the acceleration due to gravity, you can use the equation from the datasheet. I'll do that now, and then I'll show you another way of doing this question using our variables as we've outlined them here. Final velocity squared minus initial velocity squared equals 2 acceleration times distance or displacement, which means our final velocity squared is equal to 2as plus u squared. And then to get velocity by itself, square root all of that business here. So in order to use this equation, we need acceleration, distance, and initial velocity. The acceleration is from our gravitational field strength of 10 newtons per kilogram, also known as 10 meters per second squared. Our distance is the distance that he's falling through, so 3.2 meters. Our initial velocity is 0 because our boy is falling from a standstill. He's there and then just drops down into the water. Or at least by diving, we're assuming that he's just dropping into the water. Substituting these numbers into this equation, u squared is 0 squared, so that disappears straight away, giving us square root of 2 times 10 times 3.2, 8, giving us a velocity of 8 meters a second. Alternatively, if you don't want to use this equation, there is a way to do this question from another point of view. A-level physicists would call this kinematics, or the kinematics method. So we're going to look at energy transfers. When our boy drops from his diving board, his gravitational potential energy is transferred into his kinetic energy. And that kinetic energy is what's going to give us our final velocity. That way, what we do is say that the gravitational potential energy, mgh, is equal to the kinetic energy, half mv squared, which is what our boy has when he's gone from here to there. So the mgh he has up here is equal to the half mv squared he has once he's fallen that height, just about hitting the water. Before we substitute numbers in, we can see that mass is on both sides of this equation, so let's get rid of that. And then rearrange for velocity. Velocity equals 2 times g times h, or at least velocity squared was that, so to get rid of that square equals the square root of 2 times g times h, which as you notice is the same kind of calculation we've had over here. We've just reached it from a different perspective. V equals 2 times 10 times the height he's dropped by, 3.2, square root thereof, same answer as before.